Welcome to Seismic. Welcome to Equipment Seismic Isolation and Bracing. And I'm Tom Irvine. Hope you enjoy this unit today. Now we're talking about earthquakes in this series, and this is not an earthquake, but this is a space shuttle launch, and there's a mobile launch platform directly below, and there are equipment consoles mounted. And if you go to that YouTube video, you can see a really interesting video, and that equipment gets shaken as if there were an earthquake occurring. And that equipment is, I believe, mounted on wire rope isolators, but those little skirts at the bottom are blocking our view. So you'll have fun taking a look at that video, and when you do, there's two segments. And one segment, you get that pipe on the upper right, and there goes quite a bit of dynamic displacement. Got some more videos that you can copy and paste those links from the slides, and I went through the internet and found what are the best videos that I could find then that show the effect of earthquakes on equipment, indoor equipment. So please take a look at those at your leisure. So failure modes: overturning, high center of gravity, sliding, insufficient anchorage, anchor failure, tension and shear, internal component failure, cable pullout, resonant amplification, and impact with restraints or snubbers. So here's a picture of maybe some factory, for example, and equipment is toppled over and some of it is crashed into the ground. So we're concerned about what we can do to help prevent these problems, like adding sufficient bracing, for example. There's some things we can do with isolation. And here's an interesting image. It's showing the overturning risk for equipment. And it's from a paper. You can freely download that paper from the internet if you just copy and paste that into your search engine. So this is a schematic view of rigid electrical equipment in rocking motion. And view A on the left then is going to be simply supported on a fixed base. And B is going to be, and there's that little spring representing an anchor. And then this image C here is going to show that there's an isolated base, but then the equipment is just resting on the base in a simply supported manner. So isolation is good, but there should have been a restraint there as well. And we'll talk more about isolation as we go on. Now this paper at the bottom actually gives equations of motion, so you can go ahead and take a look at that paper, and you may take an action item to make a MATLAB script and come up with some exercises on overturning. And we will take a look at overturning when we get into our ASCE 7-22 units later on. So isolation hangers. So here are some pipes or ducts with isolation hangers. And it's really interesting that these are a two-way. So they're designed to reduce the transmission and vibration and noise from suspended mechanical equipment such as fans, pumps, air handling units, piping, and ductwork. So there could be, for example, turbulent flows or vortex shedding going in the fluids along those pipes. And the idea is to isolate the pipes from the building structure to mitigate the transmitted vibration from the flow-induced vibration, for example. But also, if the building's undergoing an earthquake, then these same seismic hangers would then isolate the pipes to mitigate the response of the pipes to the building vibration. So it's pretty interesting, and you can think about, for example, spring mass models and how the isolators fit in. So in this first of the two images, this would be the case. Let's say there's a system, maybe a machinery that has some rotating balance, for example, and we're concerned about the transmitted force to the foundation because that can propagate and could be base excitation for other equipment. So if we have a good isolation with a soft spring but also plenty of damping, we can mitigate those effects. We have base excitation, and it's kind of the same situation, but in reverse. We want to isolate the response of a mass, and we can mitigate the transmitted vibration then by having a soft spring, but Make sure we got plenty of damping built in. Fun stuff. So here is rooftop duct anchoring, and then anchoring then is used to limit the displacement of that duct, and is a very prudent idea. So here we've got some equipment racks, and they're mounted on different types of springs. The bottom arrangement's called a tandem spring, and then this will lower the mounted natural frequency of the equipment and help mitigate the effects of the transmitted vibration due to base excitation. These are a good idea, but with some caveats. So we're concerned about rack tipping and overturning, so we also need anchoring. Still need anchoring or bracing. Because otherwise, then this equipment could just topple over, and once the equipment starts moving, everything inside shifts and falls. For example, the support structure may deform, causing the rails to bend or collapse. The rack can be isolated, mounted via isolators, and still be anchored using seismic restrained isolators with snubbers or limit stops. So yes, we want a soft mount system, soft springs, but we also need some devices in place to limit the displacement, because we don't want the rack to overturn. So continuing on with equipment racks, then these individual electrical boxes are called LRU, for line replacement unit. And our concerns are even if the rack remains upright, the shaking moves everything inside: circuit boards, cables, servers, power supplies. Connectors can loosen, power cable disruption is a concern. Cable wiring strain, connector failures. When the rack moves, cables and power ground connections are stressed. This can pull on connectors, loosening them or creating intermittent faults. So I've got engineers that come to me and they're concerned about circuit board resonances and what levels for shock and vibration should those circuit boards and boxes, LRUs, be tested to. And I say, well, we appreciate that, and that is a concern, and you're right to address that, but it could be just something more mundane that would cause a failure, like a cable has a disconnection or something. So it needs to be slack provided for in the cables, maybe service loops or something like that, or other types of tie downs, so to avoid then the problem of having disconnections. So sometimes it's more the mundane nuts and bolts things and electrical connectors that can be the true failure mode. Not that the circuit board was excited into resonance, because a lot of those circuit boards are 200 hertz and higher anyways, and most of the earthquake energy is going to be below, say, 20 hertz or even 10 hertz. Okay, bracing, very important. So floor building movement, base isolation issues. So even if we have a well-mounted rack, then the building motion, the floor vibration, or resonance can amplify the motion. And these racks are called non-structural components. In fact, there's two chapters, or two sections within ASCE 7-22 that deal with this that we'll cover in future units. So what kind of force, and what are the shear force, the base shear force, how is that force distributed up and down that rack, and the overturning moments, etc. We will be addressing that later on, equations and so forth. So these non-structural components like racks are required by building codes to be anchored or braced in many cases. It's just also common sense regardless of what the requirement might be. The rack should be firmly anchored to the floor and or walls with appropriate seismic rated anchor bolts or braces. Okay, center of gravity. We want that as low as possible for stability. So if the center of gravity, CG, is too high, then the rack is very tall, then there is the risk of that overturning moment and toppling over. And here's just a rule of thumb from an article. Any component weighing more than 400 pounds or center of gravity more than 4 feet above the floor then would trigger the need for anchoring. Then the racks. So we want good quality racks, and rack structural failure is a possibility. So if the rack itself is not designed for seismic loads, the frame, mounting rails, or anchor points may perform a fail. This can cascade to other types of internal failures of equipment and so forth. So just think about your basic engineering, bending, twisting, stretching, shear forces, etc., compression, buckling. And it's a good idea to have these diagonal stiffening members to help reduce the dynamic loads and prevent buckling and other types of failure. So there are commercial racks out there available that have been qualified and designed and analyzed and tested to meet certain standards. We'll talk about some of those standards here shortly. So equipment racks. So here's a really interesting console or rack, and it's mounted on wire rope isolators, and it's mounted to what's called a head expander that's then mounted to an in-hole sticky shaker. Now, wire rope isolators, I fully support that idea. I think that's wonderful, but there's more to the story because we need to make sure that the displacement is limited. So there still needs to be some kind of braces or restraints or snubbers or something of that sort so that that sway just doesn't become too large, particularly at the top of that rack and so forth. So some advice here: use floor anchors designed for seismic loads, rated for shear and tensile, and rack design and seismic rating. And as I mentioned before, there are certain NEBs. We'll talk about what NEBs is in the next slide. Zone-rated racks. So these are then designed and built to withstand earthquakes in active seismic zones. One article says seismic server racks protect servers by transforming potential disaster scenarios into manageable events. A little bit of salesmanship there, but still a good point. And these racks include features such as reinforced frames we just saw on the previous slide, cross bracing, base plates, and damping and shock absorbing systems. Now, some of the standards, we're going to talk more in future units about these various standards, but we'll start mentioning one right now, Telcordia GR63. There's also other standards like International Building Code and so forth. In fact, on the next slide, so we mentioned NEBS, and that's an acronym for Network Equipment Building Systems. And the Telcordia GR63. Now off to the right is what's called a shock response spectrum. Now that's what we call it in aerospace, but in seismic sometimes it's just called a response spectrum. GR63, zone 4, 2% damping. The y-axis is peak acceleration G. The x-axis is natural frequency in hertz. And in future units, we'll talk more about these response spectra and what to do with them and how to design, analyze, and test for these types of spectra. So these NEBs and Telcordia GR63, and sometimes you'll hear the name Bellcore as well. So I think there was originally it was a Bellcore, and then now it's Telcordia, something like that. So this Telcordia GR63 core is a key standard defining physical protection requirements and including these qualification levels, and this applies to racks and cabins, cabinets, mounted electronic equipment, cable management systems, but not to entire buildings. Entire buildings, well, we have some other levels from ASCE 7-22 that will be for the entire building, but this is for the equipment inside the building. Or it could be outside the building, but they're just your non-structural type of equipment, particularly your electronics. So more on equipment racks, and got a frame, a rack unit, which sometimes called LRU for line replacement unit, cooling mechanisms, rails. Now the power distribution units, the PDUs, those tend to be heavier mass, and so those really need to be at the bottom because we want the CG to be as low as possible. So some advice here: internal load planning and mounting. This is all common sense. Place heavier equipment, batteries, uninterrupted power supply, storage, low in the rack so the CG is low. The distribution of equipment inside the cabinet in such a way that the center of gravity is closest to the bottom. Looks like we're missing some part of the sentence there. So make sure you design the distribution of equipment inside the cabinet in such a way. I think that's a better way of saying that. Use locking rails, mounts, and fasteners designed to hold equipment even under severe seismic motion. Ensure cables are managed with strains so they do not pull out under motion. Yes, indeed. Cable and power wiring management, and to secure the power distribution units, the PDUs, and wiring so they do not shift, loosen, or get pulled during motion. And I'm just thinking to myself, I've been in the rocket vehicle industry, and we've actually had some cases where, due to relative motion, there's premature disconnections of cables that actually cause flight failure. So I can perfectly understand how that concern carries over to seismic. Okay, an electrical engineering note, grounding and bonding, though more related to electrical safety than earthquakes, ensure the rack frame is properly grounded to ensure better safety and less risk of damage via stray currents. And yeah, you don't want your grounds to get broken in the event of an earthquake. So here's more about equipment racks. Now there are very good reasons why in buildings these are mounted on these raised floors. Quite a few good reasons. So the cable runs can be underneath the floor so no one's going to trip over them. There's also some really good thermal reasons for having that raised floor and that air volume underneath. But there's a trade-off, and what that trade-off is that arrangement can cause some dynamic amplification through the floor supports and on into those racks or servers. Be aware of that trade-offs. So for regular inspection and maintenance, periodically check anchor bolts, brackets, vibration isolators, if any, cable restraints. Check clearances. Racks should not impede egress or maintenance even after motion. Test to review the load. If new equipment added changes the weight drastically, the seismic rating anchoring might need to be reviewed. And as we mentioned, that the room itself, the raised floors, floating slabs can amplify motion. And we don't want that, but it does happen. And even things like the lighting, the ceiling tiles, and like the sprinkler lines, heaven forbid there's a fire. All of that needs its own type of bracing as well. So a rack might survive, but the surrounding damage from these other components and so forth may knock it offline, which is bad news. Okay, for our last slide today, we're going to take a look. We're going to switch to homes, and many of these same concerns then apply to homes in active seismic zones. So ask yourself, if the residence began shaking, what would topple? How can I secure it? So even things like lamps should be constrained. A bookshelf, desktops, your large screen TVs, tall furniture. Oh, here's something interesting for vases. So you should put bean bags of sand in the bottom of delicate containers to hold them down to lower the CG. Walls and wall mirrors and pictures hung on double hooks and heavy double-sided tape on the back to further secure. Now here's something you might not have thought of, but I would not have thought of it, but place your bed far away from the window, because in the event of broken glass, you want to be protected if you're asleep in bed. And close the blinds, because if the glass breaks, then the closed blinds can help restrain that flying glass. Keep a flashlight handy. Cupboards, secure latches on cupboards to prevent doors swinging open. Have a fire extinguisher, just a lot of really common sense things. Now, if you've got a basement, then strengthen your foundation, strengthen triple walls, prevent buckling, sliding, add plywood sheathing to reinforce triple walls beneath the foundation first floor. Store household chemicals safely, preferably near the door. Bolt down. So secure walls to foundation by drilling bolts through the sill, the wooden board directly on top of it. The seismic retrofit contractor can assess your risk, or you can do it yourself. Install flexible pipes. Get a licensed contractor to help you with that. Secure your water heater, so make sure you've got those restraint straps so your water heater does not topple over. And you also want that water heater up and running in case there's a loss of water pressure from your community supplied water, and then you can at least have the water in the water heater. So thanks for coming. Look forward to seeing you again soon. Bye for now.